What is up, Physics Squad? It's Sean here, back at you with another video. I woke up this morning and I only had one thought in my head. Why the hell is it most beneficial to use a monochromatic light with wavelengths between 500 and 700 nanometers in Young's double slit experiment? And I bet you are having the same thought too. So, in this video, that's exactly what I'm going to be explaining. With all that being said, let's get on with the video. Okay, so firstly, let's just draw a diagram to essentially explain what Young's double slit experiment looks like. Normally I would be using a ruler for this, but I'm also holding my phone, so bit impossible. So, right, let's just say we had a light source. We're going to put two slits here. We're going to say D is 0.25 millimeters, just for example. So that's 2.5 times 10 to the minus 4 meters. And then we're going to put a screen. We'll say that D is equal to 3 meters. Right. So what's going to happen? There's going to be light beams coming through each slit. And these light beams, they're going to diffract onto the screen. And what we'll see is that, obviously this is just a very rough sketch, but we do see that there are some superpositions here. Now, the reason why it's beneficial to use wavelengths between 500 and 700 nanometers is simply because of the fringe spacing, or delta Y. So, for example, if we used, let's say, a wavelength of 400 nanometers, and we use the equation delta Y is equal to lambda D over small d, and we plug that into the calculator. So we are saying lambda is 400 nanometers, which is equal to 4 times 10 to the negative 7 multiplied by big D, which is 3 meters, we said. Put all that, divide that by small d, which we said was 2.5. Here, I'll just put in a fraction. So here over 2.5 times 10 to the minus 4. What we'll get is a number that's way too small to measure, right? That's if we used a number lower than 500. And the same thing would happen, the opposite would happen if we used a number that was higher than 500. And what you'd end up with is a fringe spacing that was too large, and the light would be too blurry and too far apart to measure. Okay, now that's all over and done with. I hope you guys enjoyed the video. Don't forget to like and subscribe to see more content just like this, and I'll see you all in the next one. You thought I was done, didn't you? Bonus round! Okay, so for the wave tank using a simple harmonic oscillator experiment, the information given to us is that lambda is equal to 0.022 meters. The frequency is 15 hertz. The mass of the ball is 0.005 kilos, and that the amplitude is 0.015 meters. So, firstly, how could I accurately find the frequency? So, the way that I do it is that I first have to find t, the periods, and the way that I do that is I get a stopwatch and I'd count the number of cycles, and then I'd have the time taken as well. So we can use the cycles is equal to the time taken over the number of cycles. And we know that F is equal to 1 over T, so F would be equal to N over T. Secondly, to prove that to find the velocity, I just use v is equal to f lambda. We know that f is 15 and lambda is 0.022, so v would be equal to 15 times by 0.022, which is approximately equal to 0.33 meters per second, to two significant figures. Thirdly, to prove that the maximum vertical force on the ball is negative 0.67 newtons, first we'd define the maximum force. You could say that it's equal to m multiplied by the maximum acceleration. The maximum acceleration can be measured with omega squared a. We know that omega is equal to 2 pi f. So omega would be equal to 2 pi multiplied by 15. If we plug this into a calculator, we do 2 pi times by 15. We end up getting 94. We square that for the calculation. We get this number. Then we multiply it by the amplitude, which is equal to 0.015. We get approximately 133, and then we multiply that by the mass of the ball because of F is equal to ma max. So F is equal to 0.005 times by, and here you get 0.67. The reason why we can say that it's negative 0.67 is if we imply that an upward force is the positive direction, and we can say that when it's reached its minimum, it would also reach a maximum displacement downwards, which is why we use a negative sign. So we get negative 0.67 newtons. Okay, now the video is truly over. I really hope you guys enjoyed, and I personally think it was a 10 out of 10 performance. And if you enjoyed the video, don't forget to like, subscribe, tag 3 friends, and honestly, comment your favorite SI unit. Me personally, gotta give it up for Kelvin. You know, absolute zero and all that. Big ups, Kelvin. And I'll see you all in the next one. Bye.